continuation to our previous lecture with the Ranjakota method under module number 8, solution of ordinary differential equation initial value problems. This is now in consideration with the second type of the Ranjakota, second order of the Ranjakota, which is your higher order Ranjakota method. Under higher order Ranjakota, we have the third order Ranjakota and the fourth order Ranjakota. Remember that as we increase the order on the Ranjakota method, we are also lessening the error committed from the previous order and the previous methods, and increasing as well the accuracy of our answers. First stop is our third order Ranjakota method. Under the general form of the third order Ranjakota method, we have y of n plus 1 equal to the y naught, or initial value of y, plus the step size equal to constant value of c1 k1 plus the constant value c2 and k2. But notice we have your constant value c3 and k3 on this particular general form kasi we are increasing the value, we are increasing the accuracy, so we are also increasing the order, so we will be adding c3 and k3 on our solution. By doing so, we can then compute k3 as equal now. Same pa rin yung k1 and k2 under the general form of the Ranjakota third order method. But for k3, we will now be solving k3 as the function of x naught plus the constant value a3 times h and y naught plus b31 k1h plus, this time involving the third order, which is your b32 k2 times h. Okay, which serves as our third solution. Okay, but then again we will be using the modified Euler's version of the third order Ranjakota method. With the modified Euler's version, the y value should now be equal to n plus 1 equal now to y naught plus the step size over 6 times k1 plus 4 k2 plus k3. Okay, and that note we will also be having k1 as equal to function of x naught and y naught. k2 is now equal, dito tayo magbabago ng konti ha, k2 is now equal to the x naught plus half of the step size and y naught plus half of k1 times h over 2. And lastly, for k3, we will be having k3 by f of x naught plus h and y naught plus 2k2 times h minus k1 times h. Okay, and that is how are we going to solve the succeeding problems using the modified Euler's version of the Ranjakota method third order. So with that note, let's continue with the fourth order, the succeeding part of the higher order Ranjakota method, which is your fourth order Ranjakota method. With the fourth order Ranjakota method, the general formula for the fourth order Ranjakota method is that the y n sub n plus 1 is equal to y naught plus the step size times the constant value of c1 k1 plus c2 k2 plus c3 k3 plus c4 k4. So basically we're adding the values for C4 in K4. But in relation to that, nakalimutan kong sabihin, from the third order Ranjakota method, the values of C1, C2, C3, A2, A3, B21, B31, and B32 are basically your 8 constants. These are 6 equations that relate the 8 constants. There are 6 equations that relate the 8 constants that can be derived comparing to the given equations with the 4-term Taylor series expansion. So basically, with the 4-term series expansion, which we have already tackled from the prelim, that estimate the value of yn plus 1. So, ko-correlate lang niya yan dati. Parang dati pa rin. But again, in continuation with the 4th order Ranjakota method, where the value of K1, K2, K3, and K4, parehas pa rin naman yan. Parehas pa lang naman po yan. With K1, ganun pa rin, f of x0 and y0. And K2, ganun pa rin yan, f of x0 plus a 2h and yo plus b21 k1 h. Then K3, f of x0 plus a 3h of y0 plus b31 k1h plus b32 k2h. And lastly, involving the 4th order, we have your K4, which is f of x0 plus a4h of y0 plus b41 k1h plus b42 k2h plus b43 k3h. So you simplify that, you get the functions of x and y, then substitute to the given equation, then you'll be able to compute for K1, K2, and K3, substitute to your general formula to solve for the value of y sub n plus 1. And lastly, applying this on a modified Euler's version, the y sub n plus 1 should now be equal to y0 plus h over 6 times k1 plus 2k2 plus 2k3 plus k4. So basically, eto ngayon yung gagamitin natin for solving the value of y under the 4th order Ranjakota method. Okay, under the modified Euler's version of the 4th order Ranjakota method. Then derive for the value of K1, K2, K3, and K4 for the modified Euler's version, where again for the values of C1, C2, C3, and C4, A2, A3, and A4, B21, B31, 32, B41, 42, and B43, these are 13 constants. The values of these constants vary with the specific 4th order method. By doing so, let us try to answer an example problem involving the third order Ranjakota method. Okay, now for our example for the third order Ranjakota method, using the Ranjakota method third order, find the value of y at x equal to 0.1 if the initial value of x and y such that x is equal to 0 and y is equal to 1, and an equation of dy of dx equal to 3x plus y squared using a step size h equal to 0.05. So basically, for our solution, identify muna natin ang ating given. Initial value x0 is equal to 0, y0 is equal to 1 using a step size of 0.05. at an equation of dy over dx equal to 3x plus y squared. We are now asked for the value of y at x equal to 0.1. Yan yung ating requirement. So, for our iteration table, for the value of x plus h, y equal to y plus y naught plus h over 6 of k1 plus 4k2 using the modified Euler's version po tayo. Using the modified Euler's version. First, second, and third. Initially, x naught is equal to 0, or initial values are x naught and y naught. X is equal to 0, y is equal to 1. So plus a step size of 0.05. So 0 plus 0.05 is 0.05. And 0.05 plus 0.05 is 0.1, which will be our unknown for this problem. We are now asked to solve for the value of y at x equal to 0.1. Okay, so we still need to solve for y1 and y2. In doing so, let's continue with this solution. Using the modified Euler's version for the third order Ranjakota method. For y1 equal to y naught plus h over 6 equal to k1 plus 4k2 plus k3. We again need to solve for k1, k2, and k3 under the equation of 3x plus y squared. Remember that k1 is equal to f of x naught and y naught for the third order Ranjakota method. Substituting that, x naught is simply equal to 0 and y naught is 1. Substitute that to our equation, 3x 0 plus y squared gives us the value of k1 equal to 1. Then k2 is simply equal to f of x naught plus h over 2 and y naught plus k1h over 2. Tama ba? That was our equation, right? For the third order, solving for k1, solving for k2. So, ito yun. Yeah, under the modified Euler's version. Okay? Substitute gives us f of x naught, which is 0 plus 0.05 over 2 of y naught of 1 plus 1 times 0.05 all over 2. Okay, gives us k2 equal to f of 0.025 and 1.025. Substitute ulit natin yan dun sa ating equation, gives us functions of x and y that is equal now to 1.125625. Then solving for k3 again is f of x naught plus h and y naught plus 2k2h minus k1h. Diba? Yan yun, diba? So k3, right? This was our k3. K3 now is equal to f x naught 0, h 0.05, y naught is 1 plus 2k2 1.125 625, step size 0.05 minus k1 of 1 times 0.05. So solving for k3, f of 0.05 and y is 1.0625 60. Simplify, substitute to your equation again for x and y, gives us the value of K3 of 1.279040. So with that values known, we can simply solve for y1 as 1 plus 0.05 over 6 times the value of k1, which is 1, plus 4 k2, 1.125, 625, k3 of 1.279040. Simplify, gives you the value of y1 equal now to 1.056513. So yan lang naman yun. So y1 is 1.056513. So lastly, which is our required, the value of y at x equal to 0.1. So for y2, that is simply y1 plus the step size over 6 times k1 plus 4k2 plus k3. Again, solving for k1, f of x1 and y1, that is simply f of 0.05 and y1 of 1.056513. Substituting that again to our equation for dy over dx, which is 3x plus y squared. Substitute nyo lang dyan. Substitute. K1 is 1.266220. Then K2 is f of x1 plus h over 2 and y1 plus k1h over 2. Substituting all known values, f of x1, which is 0.05 plus h of 0.05 over 2, and y1 of 1.056513, k1 1.266220 of 0.05 over 2. So k2 is simply equal now to 1.409112. Then lastly, for k3, that is f of x1 plus h and y1 plus 2k2h minus k1h. f x1 plus h, 0.05 plus 0.05 and 1.056513 plus 2k2, 2 times 1.409112 times h of 0.05 minus k1 of 1.266220 times h of 0.05. Simplify. K3 is f of x and y of 0.1 and 1.134113. Gives us the value of K3 equal now to 1.58612. Solving for y2, which is at y of x equal to 0.1. That is y1 1.056513 plus h 0.05 over 6, and k1 was 1.266220 plus 4, k2 1.409112, k3 of K3 of 1.58612 gives us the value of y2, which is our required for this problem, of 1.127254. Okay, Ito ngayon yung ating final answer. Final answer. It will serve as our final answer for the value of y at x equal to 0.1 using the third order Ranjakota method. Sabi ko nga, as you increase the order for the Ranjakota method for your solution, we were also increasing the intensiveness of the solution needed for this type of method, but also increasing the accuracy of our answer. Kasi approximate lang naman yung method na Euler's at saka Ranjakota. So if it is an approximate, we should increase the accuracy of our answer. Given that we are not solving the exact answer, but we are approximating the actual value, and by approximating the actual value, we should also increase the accuracy of our solution. By doing so, with the Ranjakota method, we are increasing as we increase the order of our solution, we are then also increasing the accuracy of our final answer. So with that note, our final answer for y2 is then 1.27254, and again that'll serve as our final answer for the value of y at x equal to 0.1. So with that note, try to generate the general equations for the fourth order Ranjakota method under the modified Euler's version on your own. Basically, ganun lang naman yan. Paulit-ulit lang yung computation ni K1, K2, K3. Generate nyo lang based on the constant value of C1, C2, and C3. Maliban na lang kung ibibigay natin yung constant value ni C1, C2, and C3. If the values of C1, C2, C3, A2, A3, and A4, B, and B values would then be given later on in the problem, substitute nyo sila. Huwag nyo gamitin yung modified Euler's version. So with that note, that is module number 8, solution of ordinary differential equation using initial value problems. I'll see you on the next lecture videos. Bye bye.